Good morning, class. Welcome to today's lecture. Today we are going to continue with another part of direct memory access, that is DMA. Now, in part 1, we cover this session whereby we introduce ourselves to DMA. We realized that with the DMA, we are able to access the memory without involving the CPU. And we have a lot of advantages when it comes to that. So first of all, we saw that it's faster. The second thing, we saw that it saves the CPU from repetitive tasks, which is going to keep the CPU either waiting or to waste the energy resources of the CPU. So by involving the DMA, we are actually saving the CPU for other tasks, while the DMA is going to focus with the exchange of data that is between the memory and the input-output devices. So in our last discussion, we covered explain the need for direct memory access, that is DMA, and then we were able to describe the DMA operation. We do understand that the DMA operation falls under 3 modes, and we were able to look at them. And then in this session now, in this part, we are going to describe the operation of Dma controller. So it's going to almost relate to part B, but we are going to expound on part B. So we are going to look at the IC itself. Now we are going to do the recap so that we understand why DMA is very, very important before we continue with the session which we are supposed to cover today. As we know, DMA is a hardware feature that allows peripheral to transfer data directly to from memory without CPU intervention. So here we are exchanging the data between the input-output devices with the memory without involving our microprocessor. Remember that microprocessor is going to focus with other tasks, as the DMA controller is going to exchange data between the input-output devices and the memory. The input-output devices here can be a sensor which is connected to an ADC sensor. It can be a flash disk which is connected to a USB port, or it can be a floppy disk among any other input-output devices which you can connect to your computer environment. And now, because we want to exchange data, and this data is very big, it can be a large amount of data, and for us to do that within a short period of time, we have to involve another IC, which is the DMA controller. Now, when we implement this, remember it improves system efficiency by freeing the CPU from repetitive data transfer tasks. Remember, when we are exchanging data, we are not going to exchange the data once. We have to break down that data into maybe frames or packets. Then we will be carrying those packets until the whole data is complete. Remember, that one is going to be a repetitive task, and that one is not good for the microprocessor. We better leave that to be handled by the DMA controller. So when we want to implement the DMA controller in our microcomputer environment, it means that we will have to add the IC to be part of the larger computer system. And if that is so, then this is going to be a block diagram of how it's going to appear. So first of all, our master at any moment when we are exchanging data, remember the master is going to be the DMA controller. So the DMA controller is going to be connected to the input-output port, and these signals are very, very important. So we have the D request signal, we have the D acknowledge signal, we have the input output read, and then we have input output write. Those are the 4 main signals which is going to be exchanged, or the control signal that is between the input output port and the DMA controller. Remember, the port is where we are accessing our system. The only way you can access your system is through a port. And this port, I told you, it can be a physical port or a virtual port. A physical port in essence that we are able to connect the physical devices like the USB devices. A virtual port in that we can able to connect wireless devices. So this virtual port can either be a Bluetooth port or a Wi-Fi port. Now in that port is where we are going to connect our external devices. This can be either storage devices or sensing devices. Now then, between the DMA controller and our rest of the computing environment, we are going to connect the following signals, which is very, very important. The address bus signal, the memory read signal, memory write signal, hold signal, and hold acknowledge signals. These are the signals which are going to be interfaced with with our system bus. So remember, our system bus also, we have the microprocessor and the memory connected to our system bus. In microprocessor, we are going to focus with the two signal, that is hold signal and hold acknowledge signal. In the memory, of course, we have read signal and write signal. So this is going to be like write signal, and this one is read signal. Remember, I'm not showing any other signals which are involved in the process. Remember, we have the control signals from the microprocessor, which is going to enable the process to occur. Remember, the microprocessor has to initialize the process, so we have some control signal from the microprocessor. So this is a simplified overview, but it's very, very important for us to understand. So this is what is involved when we have a microcomputer environment with the DMA controller implemented. Now that brings us to another session whereby it's very important for us to understand how the DMA controller works in collaboration with the microprocessor. So the first thing which normally happens is the setup phase, and the setup phase is done by the CPU, that is the microprocessor. So the microprocessor is going to initialize the data transfer through DMA access, that is direct memory access. So CPU tells the DMA controller, so we are going to tell the DMA controller the source address, that is where data comes from, whether the data is coming from input output devices to the memory, or if the data is coming from the memory to the input output devices. And then we are going to share the destination address where the data goes. So we are going to share the two addresses, where the data comes from and where the data goes. And then the number of bytes stroke words to be transferred. This can be 16 byte, can be 64 byte. Yeah, this is the number of bytes to be transferred, a total number of bytes. And then another thing also we are going to tell them DMA controller is the type of operation which is going to do. So we have the burst mode, we have the cycle stealing, and then we have the transparent. So in burst mode, we are going to exchange data in bulk between the DMA controller and the memory and the input output devices. So it means that at this moment, the CPU is going to surrender all the buses the way I told you: the address bus, the control bus, and the data bus, for the time which we are exchanging data between the input output devices and the memory through the DMA controller. And then we have the cycle stealing. Cycle stealing is whereby the DMA is going to carry data in bits. Yeah, the reason why we have to carry data in bits between the DMA controller and the memory and any other devices which is connected to the microcomputer, it's because that in cycle stealing mode, the microprocessor also will be using that is the buses, the system buses, because at one cycle the DMA is going to use the system buses. After that one cycle, it's going to relinquish the buses back to the microprocessor. So the microprocessor will do other things at that time, and then it will return the system buses back to the DMA controller, and the process will continue. So in cycle stealing mode, just understand instead of exchanging a lot of data whereby the microprocessor is going to be idle for a long period of time, which is going to affect other operations in the system because the system bus has been taken by the DMA controller. Cycle stealing mode allows the DMA and the microprocessor to share the bus efficiently. So one cycle and DMA ndiye anatumia bus, another cycle microprocessor anatumia bus. DMA anatumia bus, microprocessor. So it means that the microprocessor also will be doing other things which requires the system bus. When that process is done, we'll return the system bus to the DMA controller. DMA na transfer another bit of data. We return the system bus to the microprocessor, and the process will continue that way. And then we have the transparent mode. The transparent mode is whereby the DMA controller is going to wait for the time when the CPU is idle. So anytime the CPU is idle, we take the system buses, we exchange the data that is between the memory and the input-output devices. So transparent mode is also is efficient, but we are not prioritizing exchange of data. We are prioritizing the processes of what? Of the microprocessor. Only when the microprocessor is idle, that is when the DMA controller is going to take the system bus and exchange the data that is between the memory and the input-output devices. Now, after the setup phase, whereby we've seen that the microprocessor is going to tell the DMA where the data is coming from, where the data is going, the size of the data we are exchanging, and the mode of operation. After that, so when the input-output device needs a DMA transfer, it sends a DMA request signal. So we are going to send a D request signal, this signal here. So D request signal to the DMA controller. When the DMA controller receives a DMA request, it sends a whole request to the processor. So anytime when we want to exchange data, the input-output devices is going to request the attention of the DMA controller. When the input-output devices is ready to exchange data, it's going to request the attention of the DMA controller through this signal, which is called D request signal. Upon the DMA controller receiving the signal, it will send a signal to the what? To the master, which is the microprocessor, and that signal is hold signal. Hold signal is the signal which is going to be sent to the microprocessor, requesting the microprocessor to suspend all its operation for the DMA to access what? The system buses. Remember, the system buses must be taken over by the DMA for the exchange of data to occur between the input-output devices and the memory. So that's the first phase. Send D request, DMA will send hold signal, and that hold signal will be received by the microprocessor. You remember the hold signal on the side of the microprocessor is connected to the ground by default. So anytime we receive a high signal in this pin, the microprocessor is going to suspend all its operation, and then it's going to relinquish the system buses back to the DMA controller. So that's the first phase. So the second phase, now after the microprocessor has received a hold signal from the DMA controller, the microprocessor is going to finish what it's currently doing. After finishing what it's currently doing, it's going to send the hold acknowledge signal. It's going to respond back to the DMA controller. So at first we saw DMA controller was telling the microprocessor, hey, I need system buses to use. Now microprocessor, before relinquishing the system buses, it will first of all finish on what it's currently doing, and then it will send the signal back to the DMA controller that actually you can now use what? The system bus. So at the end of the current instruction execution, the processor relieves the bus by asserting all its data, address, and control pins to high impedance state. Then the processor sends an acknowledge, that is HLDA signal, to the DMA controller. So after the microprocessor has made sure that it has finished on what it was doing at that moment, it will relinquish the system buses by setting all its pins to high impedance. High impedance means the pin is not either low or high state. So it means that the microprocessor cannot exchange data or cannot receive any interrupt at that moment until the DMA controller has finished using what? The system bus. Now, what will happen next? So after the DMA controller now has received the hold acknowledge from the microprocessor, it means that it is free now to continue with the exchange of data between the input-output devices and the memory. So when the controller receives an acknowledge signal, it takes control of the system bus and begins to work as a master. So that moment now, that is the only time where the microprocessor is going to be the slave and another system, which is a DMA controller, is going to be what? The master. So it means that everything which is going to happen at the microcomputer environment at that moment is controlled by what? By the DMA controller. So the DMA controller sends a DMA acknowledge signal, DAC, to input-output device. So immediately now, after getting an OK from the microprocessor through HLDA signal, the microcontroller, that is DMA controller, is going to send an acknowledge signal to the input-output devices. So it's going to tell the input-output devices, now we are ready to exchange data. So the first phase, this one requested through D request, this one accepted by acknowledging, by sending the hold signal to the microprocessor. Microprocessor acknowledges by sending HLDA to the DMA controller. DMA controller acknowledges by sending D acknowledge to the input-output devices. So the DAC signal will inform the device to get ready for DMA transfer. Now, after everything now is ready, remember we can either exchange data by reading, that is we are reading the external devices and we are writing the memory, or it can be we are reading the memory and we are writing what? The external devices. So remember, the first thing it was to request for the direct memory access transfer. That one was done by the DMA controller when it was notifying the microprocessor. Microprocessor acknowledged. Also DMA controller acknowledged the same thing to the input-output devices. That is the external devices. Now we have to exchange data, and the data I have said it can be either from the memory to the external devices or from the external devices to the memory. So let us start with the read operation. For a read operation, the DMA controller outputs the memory address on the address bus and asserts memory read and input-output write signals. The DMA read refers to the read data from memory. Hence, for a read operation, the memory outputs the data on the data bus, and this data will be written into input-output port. So we've seen for the read operation. So for the read operation, it means that we are reading data from the memory and writing it to the external devices. So for that to happen, the DMA controller is going to assert the void signal low. So it's going to assert memory read low. So this signal is going to be asserted low. Another signal which is going to be asserted low is input-output write signal. So remember, this signal is the one which we are going to use to write data to the external devices. And this signal is the one which we are going to use to read data from the memory. So anytime we are doing what is called read operation, the DMA controller is going to assert two signals low: memory read and input-output write. That is for the read operation. And then what the DMA controller is going to tell the memory is for the memory to avail data in a certain address. So there's an address which we were shared earlier by the microprocessor. So remember, microprocessor will share the address of where data is coming from, and that address is going to pass through the address bus to the registers of the DMA controller. So the DMA controller is going to go to its register and it will find the address, and that address is going to be the location where we are going to fetch data for that data to be written to the external devices. So that is about read operation. So another operation is for the write operation. So the write operation, it means that we are reading data from the external devices and we are storing the data to the memory. So for a write operation, the DMA controller outputs the memory address on the address bus and asserts memory write and input output read signals low. The DMA write refers to write data to memory. Hence, for a write operation, the input output device outputs the data on the data bus, and this data will be written into memory. When the data transfer is complete, the DMA controller asserts its hold request signal to the processor, and the processor takes control of the system bus. So for the write operation, this is where we are exchanging data from the external devices to the memory. And for that to happen, the DMA controller is going to assert the following signal low. That is the memory write signal. This signal is going to be asserted low, and input output read signal. This signal is going to be asserted low. So by asserting this low, it means that we are going to read data from the address. And remember that address we were shared earlier by the microprocessor through the address bus. So the external device is going to put the data which we want to read to the data buses, and that data is going to be written to the memory location, which is going to be generated again by the DMA controller. Remember those memory address, input output address, the size of the byte, that one was given by the microprocessor before it relinquished what? It relinquished the system buses. So the DMA controller just goes inside its registers and retrieve that data which was sent to it by the microprocessor. So remember, DMA is like a microcontroller, and you remember microcontroller iko na RAM na memory ndani yake. Now apart from having the RAM and the memory, we also have what is called registers. So the DMA registers are used to store the addresses of the input output devices or the memory. And where do we get those addresses? We get those addresses during setup phase. So during setup phase, the microprocessor shared the addresses. So we can go through this again. Let's say I want to exchange data from the external devices to the memory. So from the external devices to the memory, we'll say that is a write operation. If I want to exchange data from the memory to the external devices, we say that is a read operation. So what is going to be the first thing? The first thing, the device which wants to exchange data is going to send a D request to the DMA controller. Upon receiving the D request, the DMA controller is going to send hold signal to the microprocessor. Microprocessor will finish what it's doing currently, and it will respond by HLDA, meaning that the microprocessor has surrendered all the system buses to the DMA controller. Upon the DMA controller receiving HLDA signal, it will send D acknowledge signal to the input output devices. So this will tell the input output devices to be ready to exchange data. Now, when they are ready to exchange data, let's say I want now to read data. I want to transfer data from the external devices to the memory. And we've said that is a write operation. If it's a write operation, then we need two signals to be used. The first signal, we need to be able to read data from the external devices. And for me to read that data, I will have to assert this signal low. Input output read low. For that data to be written to the memory, I have to assert another signal law, and this signal is memory write signal. This signal is going to be asserted law. When after that has happened, the external devices is going to put data to the data bus, and that data is going to be written to the memory location. Now, what about if I want to, so that is when it is write operation. What about read operation? We've said read operation is whereby you are exchanging data from the memory to the external devices. Again, the Dma controller is going to assert two signals law. So we need to read the data. We need to read the data from the memory so that we store it to external devices. So the first thing we are going to do is to assert memory read law, and another thing we are supposed to assert input output write law. So this one will allow us to read data, and this one will allow us to store data. That is when we are now doing what? We are exchanging data from the memory to external devices, and that is what? Memory read operation. Now the IC which we are interested with is DMA, that is the DMA controller is 8237. So remember we have 8257 and 8237. So we are going to focus with the 8237. Just know that 8257 is an advanced version. Now this is an IC which was developed by the Intel to support the process of exchanging data between the memory and input-output devices without involving what? The microprocessor. So it means that this IC is also powerful. It contains 40 pins. Yeah, we have the work for different pins. So we have pin number 1 to pin number 40. So you remember, for example, we have these two pins are these 4 pins are familiar with us now: input output read, input output write, memory read, memory write. Those are the control signals which is going to enable us to exchange data either by reading the memory or writing the memory, or reading the input output devices or writing the input output devices. And then we have remember this DMA controller 8237. It has 4 independent DMA channels to service 4 input output devices. So it means that we can connect up to 4 input output devices concurrently to our microcomputer environment, because we have how many channels? 4 channels. So, and those, we have the D request for individual channels, yeah, and then we have D acknowledge for the individual channels again, D acknowledge. We have the pins which are for carrying the addresses. We have the pins which are for carrying what? Data. We have the ready signals, we have the HLDS signals, all those signals which we've talked about. Remember, you have the same in your notes. So the second part of the diagram is showing how those signals have been grouped. So we have the control signals here. Yes, the control signals again. We have the power signals. We have the acknowledge signals for the 3 channels. So you go through the notes, you'll be able to understand the work of these pins. But just understand the pins which actually we've been talking about, you can now see them. The only difference is that this 82.7 contains what? 4 channels. Channel 0, channel 1, channel 2, channel 3. Those are a total of what? 4 channels. So the number of channels can be increased by cascading any number of 82.7 controllers. So the more we need more channels, let's say if you need 6 channels, 4 channels, you need to cascade this DMA controller in series. Each channel is independently programmable to transfer up to 64 KB of data by DMA. So each channel can independently perform read transfer, write transfer, and verify transfer. Channel 0 and channel 1, that's 2 channels, are used to perform memory to memory transfer. Each channel is independently programmed to perform demand transfer (DMA), single transfer (DMA), and block transfer (DMA). So demand transfer here is the one which I told you is transparent. You wait for the microprocessor to be idle and then you exchange data. Single transfer, this whereby you allow the 2 masters to share the system bus at any given time. That is, you allow the microprocessor to use the system bus for a while, and then you return the system bus to the Dma controller for a while. So this whereby we are sharing what? The system bus. It means that this mode, we are exchanging small bits of data. Tulkana cycle stealing. This is cycle stealing mode. And then block transfer, this whereby we take control of the system bus until we've transferred a huge amount of data for us to exchange or to return back the system bus to the microprocessor. So just understand this is transparent mode, cyclic mode, and then this is that is cycle stealing mode, and then this is the block transfer mode. So this is what is inside the Dma controller, that is 82.37. This is the functional block diagram. So we have the timing and control, we have the write buffer, we have the read buffer, we have the priority encoder, we have the decrementer, we have the incrementer, we have input output buffer, we have output buffer, we have command control, input output buffer. So this is what is happening inside what? The Dma controller. So again, this one also is found in your notes. Go through them in details, understand the function of each block, but don't go deep. Just understand the main blocks here, but don't focus too much. The reason why we have these buffers is for, remember, sometimes we can have an input device which is very slow compared to the speed of the memory. So these buffers are going to hold data to match the speed of what? Input output devices, because the speed of the memory is going to be higher. And that's why we have what? The buffer. The reason why we have decrementer and incrementer, remember the data which we are going to be stored is we are going to read or write is going to be stored in successive memory location. So it means that if I have read from one memory location, the next data is going to be found in the next memory location. So, and that's when you can use the incrementer to increment what? The address. So I think that is all when it comes to 82.7. You can go through your notes in details. You will also see the explanation of these functional blocks. So ladies and gentlemen, we've come towards the end of the session. This was a very important session to finalize on what we started last session, which was online. Remember, we had a physical class also. That physical class was enhancing what we discussed in the first online lesson. So what I need now from you, make sure you go through the materials which I shared with you. We've covered this topic extensively. It is also the most examined topic in our examinations. So make sure you go through the videos. That is part 1 of the video, the notes which we discussed in the physical class, and also this part 2 of the video. But I want to share something with you so that you do understand how the DMA is finalized by the microprocessor. It's very important for you to know that we have some instructions which are normally executed by the microprocessor to allow DMA to function. So the first instruction which will always be executed by the microprocessor is the halt instruction. This halt instruction suspends the CPU operation until an external interrupt or reset occurs. Now, immediately after the microprocessor has received the hold signal from the DMA controller, this microprocessor needs to suspend what it's doing currently. And for microprocessor to suspend, all what it's doing, it has to execute this instruction, the halt instruction. In the DMA, how do we use this halt in the DMA? After setting up the DMA controller EG8257, the CPU can execute halt. At this point, the CPU is idle, and the DMA controller can request the bus via the hold signal. The 885 responds with hold acknowledge, releasing the bus to DMA, so the DMA can proceed. And then we have another operation, which is no operation NOP. So what does it do? It does the following: CPU does nothing for the machine cycle. So this one is very important when we are doing what is called cycle stealing mode. So cycle stealing mode, we are going to execute this instruction. By executing this instruction, the CPU is going to be idle for one cycle. During that one cycle, the DMA can use the system buses. So how do we use this one? Sometimes inserted in loops while waiting for the DMA transfer to complete, ensure timing gaps without altering registers or memory. And then we have another very, very important instruction, the interrupt enable instruction and the interrupt disable instruction. So how do we use this one? Before DMA starts, DI, that is interrupt disable interrupt, is often used to disable interrupts so they don't interfere with the bus handover. After DMA completes, EI, that is interrupt enable, enables interrupts. So anytime we want to leave the system buses to the DMA controller, we are going to disable all interrupts so that we don't interfere our process of handing over. And immediately after the DMA controller has finished exchange of data, we are going to enable our interrupts by asserting this signal EI, or executing this instruction, that is enable interrupts. So that comes to the end of this topic, which is very, very important, direct memory access. We've seen that direct memory access is whereby we are exchanging data between the input-output devices and the memory without involving the microprocessor. We've seen the different modes of the DMA operation. We have the cycle stealing, we have the block transfer, and we have the demand/transparent mode. We've also seen the DMA controller 82.7 as an example. We've seen the setup phase, the read operation, and the write operation. So thank you so much. This marks the end of this topic. I will continue with the next topic in our next lesson, that is from Thursday and Friday. Enjoy your day until we meet. Thank you so much.